Problem number 18, we are given this surface here. It has equation z is negative sine x sine y. X and y both are running from 0 to pi. And we're given this vector field right here, 0, 0, 2z plus 1. Here's what this surface looks like. And so part A here, there's 3 parts of the question. Use a parametrization to find the flux of F through this surface where we are orienting it pointing down. So first, we're being asked to find a parametrization. So R of x comma y, we'll parameterize this just as x and y, and then z is our function here of x and y, negative sine x sine y. And so if we do our usual normal vector, we do r sub x cross r sub y and write out the answer here. The x partial derivative of this will be 1, 0, negative cosine x sine y. We can write out the y partial derivative. And we use our usual formula to come up with the normal vector. We can just jump straight to the end. We're calling this g of xy. It's the negative partial derivative of g with respect to x, which will be cosine x sine y. It's the negative partial derivative of this with respect to y, which will be cosine y sine x, and then 1. Okay, so this is a normal vector to the surface, but the fact that we have this 1 in the third component there means that our surface is oriented pointing upwards, not downwards. How do we account for this? We're going to account for this by switching the signs here. So we switch the order that we do the cross product. That slaps a negative sign on every single component here. Negative cosine x sine y, negative cosine y sine x, and negative 1. And now this is oriented going downwards. Okay, so at this point then, we can do our usual f of r of x, y, substitute in our parametrization into the vector field. And we have 0, 0, 2 times this would be negative 2 sine x sine y plus 1. We want to do f dot product with our normal vector. So this dot product this will give us 0 plus 0 plus negative 1 times this. So that will be 2 sine x sine y minus 1. And so now to find the flux, this will just be the integral. So our bounds on x and y are both from 0 to pi. We're integrating 2 sine x sine y minus 1 dy dx. And so when you integrate this, you end up with 8 minus pi, not pi over 2, pi squared. 8 minus pi squared there when you evaluate. Very easy double integral to evaluate. Okay, so that is part A. For part B, says let E be the region below the xy plane and above S. So it's the three-dimensional region in that valley. It's the air inside the valley under the xy plane. Okay, so we want to use the integral theorem 1, use the divergence theorem here to compute the flux of F through the boundary of E with respect to the outward normal vector. So outward will be pointing down on the bottom, pointing up on the top. So our double integral over the boundary of our region E, f dot ds, is equal to the triple integral over E itself of the divergence of F. So what is the divergence of F equal to? Divergence of F here, the x partial derivative is 0, the y partial derivative is 0, the z partial derivative here is 2. So we are integrating 2 here over this region, and the bounds on the region, x and y, as before, are running from 0 to pi, and then the z bounds, the smallest z will be the negative sine x sine y, and the biggest z can be a 0. So we're integrating 2 over this region, 2 dz dy dx. And so if you crunch this out, you will end up with, so first off, when we integrate with respect to z, we just end up with a factor of z thrown in, plug in 0 will give us 0, minus what we get when we plug in the negative sine x sine y. And so this will be 2 sine x sine y here, dy dx. And so this ends up, again, I will kind of skip the details, this ends up as 8. Okay, so what's going on here? Shouldn't the, part C says your answer A and B should differ. We got 8 here. We got 8 minus pi squared here. How do we account for the discrepancy between these two things? So this is what we get for the triple integral of divergence here. This 8 minus pi squared term, this isn't the overall flux through the boundary. This is just the flux over the bottom part of the boundary. And so there is a second part to the flux. There's the flux over the top of the surface that lies in the plane, z is equal to 0 in the xy plane. And so that flux has to be pi squared. So that 8 minus pi squared plus the pi squared gives us 8. So that's how we explain the discrepancy here. Now the problem doesn't ask us to fully compute this. I'm just going to go ahead to demonstrate this, that if we do plug in, or not plug in, but we do crunch out the flux over the top portion, flux over the top part. So for that, we would parameterize r of xy is xy0, because on that top part, it's characterized by z is equal to 0. A normal vector rx cross ry. Now we want to orient upwards, and it'll just be 0, 0, 1. That looks good. And f, our integrand here, evaluated with our parameterization will be 0, 0. And now 0, 0, 2 times z plus 1, but z in our parameterization is 0. So this is just 0, 0, 1. The dot product of 0, 0, 1 with 0, 0, 1 is just 1. And so we integrate 1. And x and y are both running from 0 to pi. Sure enough, we get pi squared, and so everything checks out.